So step 101, examples class 10. Example 4, a z-test for difference in proportions. So two proportions, and our example here is about airbags. So we have a table of results from a simple random sample of front seat passengers, and we're required here to use alpha equals 0.05 to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags. So here you can see that this is a proportion test because you either have an airbag available or you do not have an airbag available. So it's a characteristic and not a mean value. So proportion test, we'll begin by letting P1 be the proportion with no airbag available. So the proportion, this is the population proportion where there's no airbag available. And P2 will be the proportion where the airbag is available. So that P1, the sample proportion P1 with no airbag available comes from 50 fatalities out of 9,800, and the sample proportion P2, where the airbag is available, would be 40 out of 11,600. So again here we're looking at the difference between our population proportions where we're doing the test and the sample proportions that we have from the data in the table. So when we're doing the z-test for two proportions, the first thing we'd need to do, again writing down here, P1 is with no airbag, P2 is the proportion with an airbag. Our sample proportions, which we denote with a hat, P1 hat, this is the sample proportion, P1 hat, that was 50 out of 9,800, very small figure here, that's 0.0051. And the sample proportion for P2 with hat is 40 out of 11,600. That's 0.0034. So those are the two sample proportions. And the pooled proportion, this is P hat, pooled proportion, that would be 50 plus 40 on the top line, divided by 9,800 plus 11,600 on the bottom line. That's 90 out of 21,400. That pooled proportion there is 0.0042. Now before we come to our test statistic, we need to make an assumptions check. Our assumptions check here relates to the sample multiplied by the proportion. So sample size 1, N1, multiplied by P1 hat, that would be 0.9800 for N1, multiplied by 0.0051, and that was 50. In fact, this is the same as our number in sample 1. So remember our assumptions check here says that that multiplication N1 times sample proportion must always be bigger than 5. That's clearly bigger than 5. N1 times Q1 hat will be much bigger than 5. That's the remainder from our first sample. N1 times Q1 hat has to be bigger than 5. So again, N2 multiplied by the proportion from sample 2, that was 0.0034 for the proportion, multiplied by 11,600. 11,600 is N2 times 0.0034. That was 39, well, in fact, close to 40. We've done a calculation there without using enough accuracy. And of course, that is also bigger than 5, which means N2 times Q2 hat would also be bigger than 5. So our assumptions checks here, because normally we'd expect to do those assumptions checks just to be sure that our samples are big enough for the z-test to be appropriate. So the z-test statistic now. A z-test statistic, and you can take this from a formula sheet, P1 hat, that's the sample 1 proportion minus P2 hat, sample 2 proportion, minus hypothesized proportion difference, D0, which we will be hypothesizing as 0 always on this course. And we divide that expression by the standard error, which is the square root of p hat, that's the pooled proportion, multiplied by 1 minus p hat, multiplied also by 1 over sample size 1 plus 1 over sample size 2. So again, quite complicated calculation for standard error. Now we'll put those numbers in from our previous slide. So we have 50 divided by 9,800 for sample proportion 1, minus 40 divided by 11,600 for proportion 2, minus the hypothesized proportion difference of 0. And we're dividing here by that pooled proportion, which is 90 divided by 21,400, multiplied by 1 minus that value, 1 minus 90 over 21,400, multiplied also by 1 over sample size 1, 1 over 9,800, plus 1 over sample size 2, that's 11,600. And, of course, that calculation, product of those three things, we'll just put the numbers down here. Now, the top line comes to be 0.00165, and the bottom line calculation, make sure you can get this, 0.000888. And so that Z statistic is 1.858. Now that's a very complicated calculation for the Z statistic, but you will always have Excel or a calculator to help you do that. Now into our template for the hypothesis test. Remember here, P1 is the proportion with no airbag. This is the population proportion with no airbag, and P2 is the population proportion with airbag. So our null hypothesis will be there is no difference, so P1 minus P2 equals 0. And the alternate hypothesis, where we are looking for an improvement with airbags, is P1 minus P2 is bigger than 0. So this is a one-sided test. P1 minus P2 is bigger than 0. Means that the proportion with airbags is greater than the proportion without airbags. We have here an alpha value of 0.05. It's a one-sided test, which means all of our alpha goes at one end. And we have here two sample sizes, 9,800 for sample size 1 and 11,600 for sample size 2. So the critical value for Z, we now have, remember this is a Z test, so we have a one-tailed Z test with an alpha value of 0.05, all at the top end of the distribution. So in order to find the critical value for 0.05 with a Z, we can either use the tables or Excel. And we're going to go through the normal table to show you how we'd find that. So we have a Z, positive Z scores normal table, and we're looking for the critical value of 0.05. Now down at the bottom end here, you can see that we've had a critical value for an area of 0.95, which gives us a rejection region 0.05. We have a Z score of 1.645. Also shows on the right-hand side of the screen with a critical value, which is a confidence level, 1.645. However you get that, that's the critical value for Z. In Excel, of course, we would be using norm INV, or norm SINV, with 0.05, or even 0.95. So 0.05, notice, gives us a negative value for Z because it's a cumulative area from the left. If we use norm SINV and 0.95, that will give us the cumulative area coming in from the left, so our right-hand end rejection region, 1.64485. So a number of ways that we can find that critical Z value, 1.645, which of course means that we reject the null hypothesis if our calculated test statistic is bigger than 1.645. From our calculations, we had a Z test statistic 1.858, which is clearly in the rejection region. 1.858, you can see, will be in that shaded right-hand end of the distribution. So the decision is to reject the null hypothesis because our calculated test statistic 1.858 is bigger than the critical value 1.645, which means in our conclusion that we have sufficient evidence at alpha equals 0.05 to suggest that the fatality rate of occupants is lower for those in cars equipped with airbags compared with those which do not have airbags. So we have evidence here that airbags do save lives. The fatality rate is lower for the airbag cars than for those without airbags. So the conclusion, in the context of a problem always, to tell the story that determines whether you have proved your hypothesis or not. Airbags save lives. And however you write that conclusion, it should make the same kind of sense as our example. Thank you.